In the late summer of 1957, the tranquil atmosphere of Toninhas Beach in Ubatuba, Brazil, was violently interrupted by a spectacle that defied the boundaries of conventional aviation. Eyewitnesses reported a massive disc-shaped object plummeting toward the ocean at an impossible, terrifying velocity. Just as a catastrophic impact seemed inevitable, the craft executed a maneuver that mocked the laws of aerodynamics, pulling up sharply at the last conceivable second. But the stress of this sudden deceleration proved fatal to the object's structural integrity. It did not merely crash, it detonated in a blinding, silent flash of light, shattering into thousands of fiery, metallic fragments that rained down into the shallow surf. This was not a distant, ambiguous light in the night sky, but a visceral physical event that left tangible, smoking evidence scattered across the Brazilian coastline. As the fiery rain hissed and cooled in the salt water, it left behind dull, irregular chunks of lightweight metal. A few of these pieces were supposedly gathered by anonymous bystanders, plucked from the wet sand before the tide could reclaim them. This simple act of collection set into motion an investigation that would pivot sharply from local folklore into the rigorous, unforgiving domain of material science. These unassuming fragments would become the focal point of the Ubatuba Incident, transforming a fleeting, chaotic aerial display into a durable scientific anomaly that would challenge researchers for decades to come. Days later, the narrative shifted from the remote coastal sands to the bustling cosmopolitan heart of Rio de Janeiro. Ibrahim Sued, a prominent and highly respected columnist for the newspaper O Globo, received a typed letter from a reader claiming to have witnessed the explosion firsthand. Enclosed with the correspondence were 3 small, highly oxidized pieces of the alleged UFO debris. The anonymous sender described the material as being as light as paper and unlike anything manufactured on Earth. In the context of the late 1950s, an era gripped by the dawn of the space age and Cold War paranoia, such a claim demanded immediate, serious attention. Recognizing the potential historical significance of the physical evidence, Sued published an account of the letter, which quickly caught the attention of Dr. Olavo Fontes. Fontes was a respected Brazilian physician with a deep, methodical interest in unexplained phenomena. He recognized immediately that anecdotal claims, no matter how dramatic, required empirical validation to hold any weight. Fontes contacted Sued and successfully acquired the fragments, determined to subject them to the most advanced analytical tools available in South America. He hand-delivered the samples to the Mineral Production Laboratory at the Brazilian Ministry of Agriculture, initiating the first formal scientific analysis of the Ubatuba material. Chemists at the government laboratory subjected the first fragment to spectrographic analysis. This technique involves burning a small sample of the material and examining the spectrum of light it emits. Because every chemical element produces a unique light signature when heated, scientists can determine the precise composition of an unknown substance. The researchers expected to find a complex alloy, perhaps a specialized mixture of aluminum and titanium, typical of experimental aerospace engineering. Instead, the readouts were startlingly simple, indicating that the metal was magnesium of an extraordinarily high purity. Initial reports from the Brazilian laboratory suggested the fragment was completely devoid of other metallic elements, achieving a purity level approaching 99.9%. In the mid-20th century, producing magnesium of such extreme purity was an incredibly difficult, highly specialized industrial process. Magnesium is highly reactive and rarely found in a pure state in nature. It binds eagerly with oxygen and other elements. To achieve this level of refinement required complex vacuum distillation techniques that were exceedingly rare and incredibly expensive. This extreme purity presented a formidable metallurgical paradox. If the object was a conventional experimental aircraft, a stray piece of military ordnance, or even a classified satellite, engineers would absolutely not have utilized unalloyed magnesium. Pure magnesium is notoriously brittle, lacking the tensile strength required to withstand the immense aerodynamic stresses of high-speed flight. Furthermore, it is highly susceptible to rapid combustion when exposed to high temperatures, making it a catastrophic choice for a vehicle's hull. We are forced to ask a perplexing question. Why would anyone, human or otherwise, construct a craft from a material so structurally ill-suited for its purported function? The physical properties of the metal directly contradicted the eyewitness accounts of a high-performance aerial vehicle. The anomaly was not just in the metal's purity, but in its profound uselessness as an aerospace building material. This contradiction became the central mystery of the Ubatuba fragments, demanding scrutiny beyond the borders of Brazil. To eliminate the possibility of a localized testing error or equipment malfunction, the investigation expanded its institutional scope. Dr. Fontes divided the remaining fragments, carefully sending pieces to various independent laboratories, including analytical facilities operated by the Brazilian Army and Navy. These subsequent military analyses confirmed the overwhelmingly high concentration of magnesium, but they began to reveal slight discrepancies in the absolute purity claims. The narrative of an impossibly pure, otherworldly metal was about to encounter the rigorous friction of international scientific scrutiny. Years later, the Ubatuba fragments crossed international borders, ultimately entering the laboratories of the Condon Committee. This project, officially known as the University of Colorado UFO Project, was funded by the United States Air Force to scientifically evaluate unexplained aerial phenomena using rigorous academic standards. Utilizing more sensitive spectrographic equipment and neutron activation analysis, American researchers detected crucial trace impurities within the magnesium. They found minute amounts of strontium, zinc, and barium, elements that were entirely absent from the initial Brazilian reports. These new findings fundamentally shifted the theoretical framework surrounding the debris. The implications of these trace elements were profound, suggesting that the metal was not perfectly pure, but rather a highly refined terrestrial product. Metallurgists noted that companies like Dow Chemical had been producing highly pure magnesium since the 1940s for very specific, specialized applications. This high-grade magnesium was not used for airplanes, but for photographic flash powder, incendiary munitions, and metallurgical research. The specific trace element profile of the Ubatuba fragments, particularly the presence of strontium and barium, closely matched the chemical signature of magnesium produced through the pigeon process. This was a common terrestrial manufacturing method developed during the Second World War to mass-produce magnesium for military applications. The American analysis provided a highly plausible, entirely terrestrial origin for the material, effectively grounding the otherworldly hypothesis in the reality of mid-century industrial chemistry. Yet, identifying the manufacturing process did not entirely close the case for those investigating the anomaly. While it provided a terrestrial origin for the material itself, it did not explain the spectacular event described on the beach. How did a large, disc-shaped object constructed of highly flammable incendiary metal end up executing impossible maneuvers and exploding over the Brazilian coast? The scientific analysis had successfully demystified the composition of the metallic fragments, but the context of their deployment remained a glaring, unresolved puzzle. Decades later, the relentless advancement of material science allowed for even deeper probing into the surviving fragments. Modern researchers turned to secondary ion mass spectrometry to analyze the isotopic ratios of the magnesium. Isotopes are variations of a chemical element that possess the same number of protons but different numbers of neutrons. The specific ratios of these isotopes can act as a cosmic fingerprint, revealing exactly where in the solar system a material was formed. Extraterrestrial materials, such as meteorites or lunar samples, frequently display isotopic ratios that differ significantly from those found naturally on Earth. They are forged in different stellar environments and subjected to different cosmic radiation exposures over billions of years. By measuring the exact proportions of magnesium-24, magnesium-25, and magnesium-26 in the Ubatuba debris, scientists could definitively answer whether the metal was forged in an alien star system or mined from the Earth's crust. The isotopic analysis of the Ubatuba debris yielded results that were starkly and definitively terrestrial. The ratios of the three magnesium isotopes matched the standard distribution found naturally on our planet with absolute precision. This data struck a heavy, insurmountable blow against the hypothesis of an extraterrestrial origin, anchoring the physical evidence firmly to our own world. The fragments were undeniably manufactured here, subject to the exact same physical and chemical laws as any other terrestrial alloy. Despite the conclusive isotopic data regarding the metal's origin, a profound shadow of uncertainty still loomed over the historical event itself. The original letter writer who contacted Ibrahim Sued was never identified. The eyewitnesses on Toninhas Beach were never formally interviewed, their accounts never corroborated by official investigators. The chain of custody for the fragments was fraught with vast, undocumented gaps, raising the very real possibility that the pieces mailed to the newspaper were entirely unrelated to any aerial explosion. They could have been scavenged from a forgotten military test, an industrial accident, or deliberately manufactured as a complex hoax. Nevertheless, the rigorous testing of the Ubatuba fragments marked a critical turning point in investigating unexplained aerial phenomena. It demonstrated a necessary paradigm shift, moving the field away from relying solely on subjective human memory and easily manipulated anecdotal testimony. The focus pivoted toward the objective, quantifiable, and unforgiving realm of the physical sciences. The incident proved that alleged UFO evidence could be subjected to the scientific method, tested, measured, and debated within the established parameters of metallurgy and chemistry. This case study established a vital precedent for all future investigations into the unknown. It highlighted the absolute necessity of maintaining a strict chain of custody and the critical importance of utilizing multiple independent laboratories to verify extraordinary claims. The echoes of that early research persisted, serving as a foundational lesson in scientific skepticism. Ultimately, the Ubatuba incident stands as a powerful testament to the enduring process of scientific inquiry. While the recovered debris did not prove the existence of otherworldly visitors, it sparked a vital, decades-long debate about the limits of material science and the methodologies we use to explore the unknown. The pieces of magnesium, once thought to be the shattered hull of an alien craft, became something arguably more valuable. They served as a catalyst for rigorous intellectual scrutiny, transforming a wild coastal legend into a lasting scientific puzzle that forces us to refine how we search for truth in the shadows of the unexplained.